Okay, hello. Welcome to Lecture 8. If you don't recognize me, I'd understand. I'm Osher. I've been behind the scenes this whole time mostly. I just showed up for the very first lecture where you saw me. I'm going to be talking about control theory today. And I'm hoping this lecture is going to be pretty interactive because we're going to have a live demo where we're going to try to figure out we're going to try to derive the algorithm that we'll be using in the homework. So, yeah, previously, this whole task that we've been trying to do in this class is self-driving. Get a car from point A to point B autonomously. And we've seen how we can use computer vision to extract an occupancy map from our view through the camera, and how we can use path planning to take that occupancy map and generate a trajectory of points that we should follow in order to get from point A to point B. So today, we're going to be talking about control theory. Given this list of points, how do we follow them? What should we actually set the steering wheel to? What should we press the pedals at? What should be the physical outputs that would follow our path? And my goals for today's lecture are to get you familiar with the framework of what control theory is and understand two algorithms that we're going to look at, PID and LQR, which are different approaches to the problem. We're going to apply this to self-driving cars in Duckytown, and I want to show you what the math of control theory can look like. It's a huge field, and I think it's super cool. And I've definitely spent a lot of time in the rabbit hole of just like looking up control theory things. Although the math itself is not going to be critical for our work, it's just cool in its own right. So if you're curious, I can send you more stuff and you can look into it. So don't worry if some of the technical math stuff doesn't catch. Okay, so we need a plan of attack. We have a problem. We have our input, a list of waypoints, and we want outputs of what our physical outputs are. So much like we did every other time, we want to sort of figure out how to phrase our algorithm such that it can solve this task. And as like mathematicians and programmers, what we can do, so first we need to formalize our inputs and outputs mathematically, and so we can, what are the exact objects that we'll have as inputs and outputs, when do we take inputs and when do we output them, and then we define a cost function and minimize it. That's generally the approach to engineering tasks in this realm, because we know how to minimize functions. So if we can define a cost function and minimize it, then we'll have a good algorithm. Okay, so let's formalize control theory. What are the components? So I'm going to split this up into three things: a goal, a state, and an action. A goal is going to be our desired outcome. So let's say in the case of our task, which is driving a car around this map, what would a goal be? Like, what information would you have to convey the goal? What would be the numbers? And feel free, if I ask questions, feel free to post them in the chat, or ask questions in the chat. Or unmute yourself and talk. There's not that many of us, we can just talk. So like what would you have to tell me in order to tell me what the goal of our self-driving car is? Any thoughts? Oh, I just spoiled it. Okay, well, yeah, so the goal here would be a coordinate. It would be a position on the map. We want to get to a specific location. And we formalize this by saying it's a vector of numbers, an x and y coordinate. And although there's other factors that we'll see in the state, really what we care about is just the x and y coordinate. So we have a state. A state in control theory is a sufficiently predictive description of the system. And this bit about it being sufficiently predictive will come into play later in the lecture. But basically, this is a description of what the state of the system is. That's enough information to be able to predict how the system will evolve. So this could be things like a position, an orientation, and maybe some velocities. Depends how specific we want to be. So if we want to know the state of the car, we need to know not just where it is, but also where it's facing. And if we want to know the state more specifically, we need to know the like individual wheel velocities, or just the forward velocity and the rotational velocity. And we can get as specific as we want, and we'll see that that has different outcomes. So state is more descriptive than our goal is in this case, but we want to match certain elements of the state to our goal. And we can reparameterize the state in different ways, and it would be equivalent. And then an action is the direct physical outputs of our system. In our case, if you'll remember back to the first weeks of lecture, what do we output? What is the output of our whole system? What do we give the car? Oh, I keep clicking it and then showing it. Well, yeah, might as well just show it. So we had our car interface, the way we actually interface with the car. And at the end of the day, we're going to be, or at least for this task, we're going to assume we're going to be outputting a steering and a throttle, which are numbers between -1 and 1, which correspond to how much we would depress the pedals and how we would turn our steering wheel. So these are the three components. This is how we formalize all control tasks. And here are also examples of what specifically they would be in our task. But we have a state, a goal, and an action. Okay, so now that we have those, where our algorithm fits in is here. It's going to be a function that takes in a state and a goal and outputs an action in order to reach the goal. So it's going to be, the whole thing is going to be inside of what we call a control loop, which is going to be running this function many times, like once every few milliseconds. And it will output that action into the environment. The environment will change. It'll reobserve the state and then recompute what action it should take. And this would be the control loop. The goal can be constant or change as well. So for example, if we have a waypoint, we might just set that goal to be constant until we reach that waypoint and then update the goal to be the next waypoint. So this is what a control loop is. And what we want to program is this control algorithm. And we also want to implement the entire control loop, but we want to think about what kind of algorithms can we use here to decide which actions to output. Okay. So let's solve this with math. So how do we design algorithms? Well, I was talking about minimization. We know how to do minimization. So we need to define a cost function and then minimize it. And that theoretically should be what our algorithm is. Yeah, minimizing cost function, this is all we know how to do, all I know how to do. So let's define an error, a cost, given our goal and state, and find the action that would bring that to 0. Okay, so that's pretty vague. Now I'm going to go over to a demo to actually try this out. Because this is vague because this is a vague description, so it can fit many different tasks. And we'll see, I'll do an example with a self-driving car. And we'll see how that goes. So here I have a notebook, which you guys now have access to. Or yeah, should soon. Where I'm just going to initialize this environment, a DuckyTown environment. We're going to look at it. And I'm using a custom set of physics. This is not the same physics you'll be using, where they're inspired from DC motors, but it's not really relevant. This is just to illustrate how we can fit this control algorithm to different physical systems. So here I'm using a custom set of physics. And I'm going to initialize this environment and let me know, you can see this thing. Can anybody give me a signal? You can see the car on the map.
Yeah, we can see that.
Dope. Okay, and this is a custom map I made just for testing purposes. So we have this, and we want to determine our task. We have a goal and a state. So in this case, let's say we want to reach this finish line, which is at coordinate 3.25. So we can find the goal will be x equals 3.25, and we can just say our state is our x position. So we're going to reach the state by reading a sensor. In this case, we're just going to literally go into the environment and have it tell us what our x position is. In reality, you would use a sensor to estimate your state. So we have a goal and a state, and now we want a control loop. So I've prepped this control loop here, which will loop a bunch of times. And at each point, it's going to compute an action after reading a state, send that action into the environment, and then show what happened. And let's try running this. And our car is like off screen, but we can see that our position is not changing. Our speed is 0. We're not making it to the target. And that happened because our action was just 0. So we want to control if that actually does something. So let's try and do that. So what we have at hand is a goal and a state. And we want to compute an action. So first thing I'm going to do is just to show you how this works. What if we make our action 1 and run this? Well, now we're giving it a constant throttle and we're accelerating forward. Awesome. Here I'm going to graph some terms. You're going to be seeing this graph a lot. And what it is basically we're graphing over time steps. We're graphing our action, our state, and our goal. So we can see our action is constant at 1. Our goal is at 3.25, and our state started close to 0 and is now accelerating towards the goal. We made it, but then we totally passed our goal. Okay. So this is going to be a problem. We're just going to keep accelerating forever. So let's try and fix this. Any thoughts? What should I make my action? I have access to a state, which is a number, and a goal, which is another number. Ideally, I want my action to depend on the state and the goal, not just be a constant number. I don't know. What are your thoughts?
The goal minus the state.
That is a fantastic idea. Okay, you're already ahead of what I was meant to do. Yeah, let's do goal minus state. So what I'm going to define this own variable here, which is I'm going to call it air. It's going to be goal minus state. I'm going to say the action is equal to the air. And you'll see why I made it its own thing soon. Let's try this. Okay. Now we're going very quickly. We can see as our state is getting closer to the goal, our action is getting smaller. And once we pass the goal, our action is now negative. Now we still overshot, but you can see our speed is slowing down here because we are giving it an inverse throttle. Yeah, our state is flattening out, and eventually we'll probably turn back and make it back to the goal. So awesome. We're not going to diverge to infinity, but we're still not doing so hot. But this is a great idea. If we can define the error as being a number, positive or negative, that's proportional to the distance to the goal, if we make our action proportional to the error, then we can basically change directions and change how much we're pushing depending on how far we are and which direction of the goal we're on. And this oscillation is pretty natural for, this is what we call a proportional controller, because it's proportional to the error. Okay, but we want to do something to mitigate the fact that we just overshot by a lot. And now we made it back, and once we reached the goal, only afterwards did we stop and turn around again to have a positive action. And this oscillation is probably going to continue for a while. Okay, any ideas about how we can mitigate this overshooting? And this is a hard question, so. And feel free to text it or say it. Ran out of time. What we have here is currently we're using the present error to determine the action. But what's happening is that if we are only using the current state, we might overshoot and not take into account that future states might do worse. So if we have a velocity coming in when we reach the goal, our action will be 0, but we really want the action to be negative so it can counteract that velocity. So we don't just want to reach the goal, we want to stop at the goal. Okay, so, oh, let's check. Awesome, that's a fantastic idea. Okay, Jake said use current velocity in the calculation. What should I do with the current velocity? First, let's compute the current velocity. Well, how can we do that? We need something more than just this, because here we're just running a computation on the current information. We need to keep track of what happened in the last state and use that to compute the velocity. So let me make a variable. I'll call it last error. And let me initialize this at goal minus read sensor. Okay. And what we can say is if we update here, last error, error. So now we're keeping track of what the last error we measured was. So we have the current distance to the goal and the last distance to the goal. And we can compute velocity by saying it's basically the derivative of the error. We have it's going to be the difference between the current error and the last error. And as a good derivative, we'll use dt. I think we have 30 frames per second, so I'll say my or in simulation, at least. That's 30 ticks per second. So I'll say my dt is this. Okay. So this should give us a velocity. If we can see what our current error is and what our last error is, if our current error is much smaller than the last error, that means we're reaching the goal very quickly. Then the derivative error will be very high, or a very large negative number if error is less than last error. So if d error is a very large negative number, that means we're going towards the goal very quickly. And if it's a very large positive number, that means we're going backwards. Well, we don't know if it's towards the goal or away from the goal, but we're going backwards very quickly. So suppose we're here. We are approaching the goal and we have a high velocity. That high velocity means the d error will be a very large negative number. How should I use d error to change action? First of all, should action be smaller than it is now or larger than it is now? Which direction do we even want to change action in?
We want it to be smaller, so we should add it.
Perfect. Yeah. Handling the signs here is a little confusing, so I'm just trying to be very explicit about it. But yeah, exactly. So if we add it, then that means if we're approaching the goal very quickly, this will be a large negative term and it'll slow us down. Oh, oops, that's the wrong place. We want our action to be this. Okay. Let's see what happens. Pull this up. Okay. So the beginning looks pretty similar, albeit a little curvier than the linear thing we had before. We have our state going towards the goal. And as we're going towards the goal, it's still overshooting by a lot. Let's display these more clearly so we can see what's going on. I'm going to add a term d error to the plot, and I'm going to merge the state and the goal into one thing so it's less cluttered. I'm just going to plot the error, which is the goal minus the state. And this might be useful later. This might be useful because derivatives get funky if we just compute them naively like this. So I'm just going to cap these. We'll say this is the max of the min of d error, comma, let's say, sure, 3 and minus 3. So just in case we get weird large numbers, you don't freak out. Okay. Let's plot this, see what's going on. So now we have the blue is our error, and we want to get this to 0. The green is our action, and the orange is our derivative error. And the action is just the sum of these two. So we can see that the action, if we had just taken error, our action would be much higher than it is right now. But this distance is not enough. We want the action to turn negative already earlier. Oh, this is pretty nice. Our error is going down to 0, and we just overshot it by a bit. Okay, that actually worked pretty well. Awesome. So we're overshooting by a very small amount relative to what we were doing before. Now we're turning back. So how can we get this overshooting to be even smaller? Well, we can tune these with constants. We can say let's have a proportional term with a constant for a proportional term. It'll be 1. A derivative term, let's say that constant is 1 for now. And we'll weight these according to these constants. So if we wanted to slow down earlier, we wanted the derivative error to have a bigger effect. So we can turn up this constant and say it's like 1.4, and then see what happens. Hopefully this plot makes sense. I've been reading a lot, so I know what's going on, but let me know if you have any questions about what's happening on screen. This is also pretty slow frame rate for some reason. My computer is not having it. Okay, so now our action already became negative way back here. And our error is approaching 0 and slowing down preemptively. This looks pretty great. Okay, we're still overshooting, but really not by a lot. And we could keep doing this forever and get better. But I mean, that's not super important for this demonstration. But yeah, okay, we have an algorithm. This is awesome. Let's try controlling a different goal in a different state and see how this does. What if instead of controlling the position, we controlled the velocity? Let's have one of these. And let's say I want to get to 0.75 meters per second. And I want to maintain that speed. And now my state isn't going to be position, it's going to be a speed. Okay. So this is a nice graph. So error here went to 0. It just oscillated briefly. And this is a pretty well-tuned control algorithm. Ideally, there's no oscillation. Thanks. But this is great. Before we had a lot of these oscillations that were very big. So we've converged to our goal. So now if we try this with velocity, we can use the exact same algorithm. If our error will represent how much lower we are, or if our goal velocity is much higher than our current velocity, our error will be positive and we want to throttle more. If d error might still be useful. So the nice thing about this algorithm is that it's very general. It works for different systems, even though velocity operates under a different set of physics than position. Let me initialize this to just the proportional term, and let's see how this does. So now we're not trying to reach the finish line. We're just trying to reach 0.75 meters per second and stay there. So our action is exactly our error. So they're both on one line because we just define action to be the error. And we can see that we've reached 0.48 meters per second, and we're sort of flattening out down here. And this is a problem. Why aren't we making it to 0.75? We're not having the problem we had last time, which is that we were overshooting. And if we could add this opposing force to counteract overshooting, but we don't have overshooting now. Now our issue is that we have that we're not even getting to the goal. We're constantly at 0.53 when we want to be at 0.75. And this is a common issue in many systems. It wasn't apparent in our last system, but if we added friction or stuff like that, it might have changed. So we need to add something else here. What happens here is if we're at 0.53 constantly, then our error has reached a constant number. It's about 0.2, which means our action is roughly constant at like 0.2 throttle. But 0.2 throttle might correspond to this velocity. And we need a higher number to reach the higher velocity. So whatever we do, just using something like error and d-error isn't going to be enough in a system where a constant error won't lead to change. Okay, so what can we do about this? Any thoughts? We have this prolonged error. Oops. We have a prolonged error, and we're never reaching our target. What kind of actions can we take to deal with this? well, last time we added a term here. Ideally, if we can add a third term that would fix this problem, then we'll be good. But what kind of thing can we use for the third term? And it may or may not begin with an I, since you might have noticed we have a P term and a D term. And the algorithm is named PID.
Something to do with an integral.
That's an excellent guess. Okay, integral. So what would we do with an integral in this case? What should I integrate?
Maybe the error in V.
I like it. Okay. Let me integrate the error. Okay, so I'm going to keep a tally of the total error. Started at 0. You said integrate the error in what?
I said V if we're controlling for V.
Ah, oh, I see. Yeah. Okay. By the way, since I failed to set this up with a Zoom Pro account, we're going to switch to another meeting in 10 minutes. I apologize for that, but I'll update the Piazza post that you used to get here with another link, and we'll just hop right back on. So, yeah, sorry about that. Yeah, so our error is in V, and we just want to integrate that to get sort of the integral of what the difference in velocities is. So at every time step, how do we do integrals? It's dt. So we integrate, we'll add the current error times dt. Okay, now we have a tally of an integral of this error in our velocity over time. And what should we do with this total error? Should we add it? Should we subtract it? Let's add another constant. AI times total error. So if our total error is a positive number, it means we have been going, say, too slowly in this case. Our velocity is below what it should be, and we want a higher velocity. So should we add total error or subtract it?
Let's add it.
Let's add it. Okay. Well, awesome. Then we'll have a positive I term. And let's say, let's throw in a number. Since this is probably going to be a pretty big, since we're adding these numbers, this number a bunch of times, this might be a pretty big number. So usually your I term, your I coefficient is going to be pretty small. Let's do total error. Bam. Okay, we have our total error. Actually, I'm going to plot this as like over 10 in case it's too big, so we don't lose sight of what's going on in the plot. Okay, so we'll add this. I'm going to set a constant, make it pretty small, and let's see what happens. So this, we settled at an error of 0.2 last time. Now if we run this again, our total error is now in green and our action is in red. Notice I'm keeping the D term at 0 because we don't need to dampen any oscillations yet, which is the reason we had the D term. So our speed is 0.56. Okay, that's a little higher than what it was last time. I'm going to cap this at even a smaller thing so it's even more visible. So we're still going up. We're a little higher than what we were last time. 0.59. Yeah, last time we converged at 0.53, and now we're still going up. I think we should add more I. We made it 0.6. Okay, we're getting closer. Let's try something larger. And okay, we're at 0.58 meters per second. Our action is going up, while our error is not going up, and we're not even using the error. We can see this green line, total error, is slowly increasing, and this action is increasing due to the increase in total error as we accumulate an integral of error. And as time goes on, this total error will get bigger, and so will our action, which will speed us up. And eventually, we'll reach our target. Our car's going to go off screen, so we're not going to be able to see it anymore. But our error is continuously decreasing it to 0. We could even increase this further, probably. The issue with having a large I term is something like, let's say we have reached our goal, and our error is at 0. We might still be pushing it because we've had so much previous error. We might still be telling it to keep going even faster from the I term. So it's dangerous to have a large I. And what people will normally do is they'll have a rolling slider, which is instead of tallying the integral of all error in history, it'll be like the error of the previous like 100 time steps or something. And eventually, after you overshoot, then you're going to have negative error, and the integral is going to go down, even if you don't do this. But a rolling slider helps mitigate that overshooting. And look, our error is getting to 0. Our speed is 0.74. Blam. Okay, and we finished the time allotted to this control loop. So we just implemented what's called a PID controller. It's exactly, the nice thing about this is that it's pretty intuitive. If we define an error as just the goal minus the state, we can get these 3 terms. One term to basically push more the further we are and in the direction we need to go. One term will be the derivative, and this counteracts large velocities. So if we have a large velocity, it might just be overshadowed by a large error. This term might be bigger. But if we have a small error and a large velocity, then this term will dominate, since this term will be pretty small, which means when we're close to our goal, we're going to counteract velocities, which is going to stop us at our goal. And finally, if we have constant errors, like if we're trying to match a velocity or something like that, then we have an I term, which will correct for consistent errors that we didn't account for with these two. And that's what PID is. It's pretty neat. It's pretty concise. And it's super useful. And yeah, and you can access this notebook in the control folder. Yeah, okay, we did that. Let's talk about it. Oh, I should probably stop it. It stopped. Okay. It is. Okay, I should speed up. So we have PID. PID is as an algorithm looks like this. U being an action, U being an error, and we have these constants. And we just talked about this. And to get PID to work, you simply implement this algorithm for whatever your state is or whatever your action is, and just tune the constants if the system changes. Like if we're moving to velocity or if we have a different car, we can just tune these constants. And this is what engineers do all the damn time. So in DecuTown, we need to think about this was a toy example. We're trying to match a velocity or position. But really what we're trying to get is to these 2-dimensional waypoints. We have a car. This is originally a picture of a sailboat, but I'm labeling it car. And we're trying to follow these waypoints. So we need to formalize error here, something we can do PID on. So the question is, what should our error even be? Before we had it be like the difference in velocities or the distance to our goal. Any thoughts about how we can, if we have waypoints and position of the car, what should our error be?
Maybe x coordinates minus y coordinates of the car and the point that we want it to go to.
That's a fantastic idea. Yeah, so in general, what we end up doing when we have like multiple dimensions of states and goals, we just do it along each dimension. For our case though, because the car operates on a more of like a forward driving and a turning model rather than like an X movement and a Y movement, we can't control this independently, but we can control forward movement and rotation somewhat independently. We're going to be formalizing this as more of a how much to turn and how much to go forward. But yeah, that's the exact idea of how we can expand PID to more dimensions. So let's see. We need to figure out how much we should turn. And one idea to do that is something called, my talking points, is called cross-track error. We can measure the distance from where we are to where we should be by interpolating from the waypoints. That's our track. And we can measure the distance. And the bigger this distance is, the more we should turn towards the track. And this is also a signed number. So it can be positive on one side and negative on the other side. so that we can turn one way on one of the sides and the other on the other. And this can be useful for, we can compute a line between the 2 points, measure the distance of the center of the car to the line. This is cross-check error. It's super useful. We can also equivalently do, somewhat equivalently, we can measure, sort of look at where we're looking at the heading of the car, what orientation it's in, and we can look at where the next waypoint is, and we can find the angle we should have to turn to look at the waypoint. And that would be sort of a similar measure of how much we should turn to get back on track. But it uses just the final waypoint instead of where we are in the track. Okay. This was, if the demo didn't go well, I was going to talk about this. This is talking about PID on cross-track error, where we have like derivative is opposing proportional gain. We have this oscillations that we saw. These slides are also going to be available if you want to see them. You can see what behavior with high I or low I. Like if we have high I, we would have those oscillations I was talking about, which we want to avoid. But we saw this in the demo. We have one error which we measured, which is we want to stay on the path. We want to correct if we're off the path. We want to correct our steering, but we also want a control loop to progress along the path. We want to move forward. So we can parameterize this using different errors, much like cross-track and angles. We can look at, say, the desired velocity. We want to be cruising at a constant speed, and this can depend on a lot of things. Another formulation of it could be, what's the distance to the next waypoint? And then once we get close enough to the next waypoint, we simply update what the next waypoint is to the next one. And these are different ways to formulate the problem. You're going to be doing this on your homework. So you're going to choose one of these or whatever you've come up with, and come up with 2 control loops, one for steering and one for throttle. What the errors should be. Alina, you're allowed.
Sorry, I forgot to mute again.
No worries. So, yeah. So you can use the car's position and a waypoint to compute these, and then throw that into your PID loop as the error. Okay. Cool thing about PID, we can use it for a whole ton of systems. We can do the same thing with a robotic arm, where we just plug in a different goal, state, and action. And like we can have a different target. The target is like the end of the arm. The state will be the angle at each of the joints. The action will be voltages for each of the motors. And we can use this and figure out what the error should be and run PID on it and just tune the constants and it'll work, which is the great thing about PID. It works for so many systems. But it doesn't always work very well. So one example is, say we're doing cruise control. If we're trying to maintain a speed or a distance behind a car, and our action is something like the gas pedal, we can look at what would ideal behavior look like. Well, that's when we have our error is constantly 0. That's perfect control. What would PID do in this case? What would PID do in this scenario? Well, and I'm sort of leading you to see why PID isn't a great choice of algorithm for this case. So what would the PI and D terms be? If our error is always 0, what's our P term? Feel free to chat or say anything. So suppose we are driving perfectly and we are maintaining the exact target speed. That would make the difference between goal and state 0. So the error would be 0, and our P term is just proportional to error. So the proportional term would be 0. If we look at the derivative term, since we have a constant error, the derivative of it will also be 0. And the integral of it will be 0 as well. So in this case, all 3 terms end up being 0 if we're behaving optimally. And what that means is our action is 0. And this is where the problem is. If our action is 0, we were going to release the gas pedal completely. And what that would mean is that the car would go to a standstill. It would divert off of this optimal path, optimal control. Sorry. So yeah, action would be 0. So PID, the I term can sort of correct for this, but PID will always be correcting for its mistakes. It's going to be lagging behind and then correcting for it, rather than doing it right completely. Optimal behavior is not stable under PID in a system like this. In the system where we're trying to reach a finish line and removing your foot from the gas is perfect if you're at the goal, works, but PID doesn't always work for every system, or it's not very natural to pick. And we can observe this mathematically with control theory, and this is out of scope. Using classical control theory, you can sort of convert these problems into something called phase space and basically model the behavior of your controller, your PID controller, as part of the physics of the system. So if you can model what the physics of the system are, and you model your controller as something that is just a part of the physics, you can sort of predict what kind of behavior the system will have, like if it's going to have oscillations or if it's going to be stable or unstable. And we can find mathematically from that things like edits to PID. If we add another integral term, the integral of error, this actually mitigates this issue in this case. And I'm not going to go into that math, but it's pretty cool that we can do mathematical analysis on this. But PID does not really derive from mathematical analysis. It derives mostly from intuition. So how can we do better? Remember, this is our control loop. What time is it? Okay, I should really speed it up. So with PID, we handpicked some terms on our error, and we got an action from that. But it's sort of like a zip tie. You can throw PID at any problem, and with enough tuning, it'll do okay. But we want to do better. So yeah, PID sometimes fails. What does it even mean to do better? Could we measure that? What would a better algorithm look like? Like, instead of just designing another algorithm, we first should design a sort of measurement of what a better algorithm is, and then we can find algorithms according to that metric. Okay. So how do we define betterness as a theme of like programming mathematical problems? Sort of you might recognize it as my take on engineering, what I mentioned at the beginning of the presentation. What mathematically can we use to define the performance of our algorithm? So what I'm getting at is cost functions. Optimal control is what the best control is the control that minimizes some cost function. And if we want better control, we need a more directly correct cost function that actually represents what we mean when we say better. So in PID, we were sort of trying to get error to 0, which we do want, but we also have other considerations. So one consideration is we don't just want to get to the goal, we want to stay at the goal, and we care if we overshoot, which we didn't encode in PID. We just said get error to 0, get the current error to 0, and it did that, but then that made future errors really high. So we sort of somehow want to incorporate the future errors into our costs, not just the present one. However, if we just do this, we're gonna get some undesired behavior. Say, if we want to get to a goal, and we sum up the future errors and we try to minimize that, the optimal control for that would be press the throttle like way beyond its limit, accelerate by like 1,000,000 Gs, and then once you get to the goal, slam on the brakes. And that would work. That would minimize your distance from the goal over time. But clearly that's not optimal behavior. We want something better than that. So how can we encode? We need our cost function to not just incorporate the difference between our state and our goal. We need to incorporate something else. And what could that be? So the goal here doesn't actually determine our entire cost function, where we want to be. We also care about how we get there. And one thing we can use, the only thing we haven't used yet, other than our goal and state, is our action. So what we could do is we could penalize actions. We could say, if you have a really large action, like pushing the throttle really, really hard or slamming the brakes, we could penalize that as well. So that optimal control will both minimize the error as much as possible while using gentle actions. This is useful for a bunch of reasons. If you want to be more efficient, if you want to use less gas, if you want to have a more gentle ride, stuff like that. So in general, we will penalize both states and actions, and we will define this cost function. We have a cost function that depends on the state and the action, and we were trying to minimize the sum of it over time by picking what our actions are. So here, from now on, you'll see X and U a lot. X will be our state, U will be our action. So now we have a minimization problem. All we have to do is assign the cost such that the thing that actually minimizes it is what we want to happen, is optimal control. So one thing we can do to do that is we can weight different measurements and actions differently. Say we really don't want people slamming on the brakes, but it's okay if they like open the window. If opening the window is like an action, we don't need to penalize that so much. And say we want to really penalize being far off from the path, but say our Z coordinate, our vertical height of the car is not really something we want to penalize either, because we don't really have control over that. So we can, in our C cost function over here, we can incorporate different weights for different elements of the position and or of the state and action. Yeah. Okay, so what we're going to use is something called a quadratic cost. We're going to use, these will be vectors. We have a state vector with like the position, the velocity, the orientation, etc., and the action, which will be like the steering and the throttle. And we're going to have matrices that will give us, these are going to be positive semi-definite matrices, which is not super important. But we basically want a cost that's positive, and it's going to be quadratic on these terms. So it's going to be a cost that's proportional to like the error squared. And we can determine exactly how that proportionality works by having different coefficients inside of these matrices to weight different parts of the state and action. And usually these are going to be diagonal matrices, which means each dimension of the state and each dimension of the action are weighed separately. We can also have cross terms, but those aren't really important. Okay, so let's talk about dynamics. If we want to be able to minimize this, we want to choose the best actions. We're missing something. We're optimizing over XTs in the future, but we don't know what the future states are. We can only measure the present state. So in order to optimize over the future states, we need to be able to sort of predict what they will be. And this is really critical. One thing that PID did is it didn't really take into account physics. It just sort of went for it. But if we can sort of model the physical system, we can predict future states, and that will lead to things like avoiding overshooting, which we couldn't do with PID because we didn't really know what the behavior would be, or we can only do it naively. And this is why I said the states must be sufficiently predictive. We need the state to be informative enough that we can use it to tell what the next state will be. So we're going to define this. We're going to say the future state is a function of the current state and the action. You're not only, so say if you have your position will determine your next position, and so will the amount of throttle you give it. And what we're going to minimize now, instead of minimizing a bunch of XTs, we're only going to use X1, the present state, in our minimization problem. And we're just going to say X2 is a function of X1 and U1, and X3 is a function of this and U2. And we can keep doing this such that predict all future states. And this just depends on the actions and our current state. And this is a minimization problem we can actually compute because we have access to all of this. Okay, so we're going to deal with, famously, I mean, this optimization problem is much easier when you have linear dynamics, which means this equation, predicting the next state given the current state, is a linear equation. And these are vectors and matrices. But it won't always be. And when it's not, what we do is we linearly approximate whatever the dynamics are. We can use the gradients of f with respect to x and u to create a tail expansion around some certain states and actions and find the linear approximation of those. And that will basically, we can approximate nonlinear dynamics with linear dynamics. Okay. Anybody have any questions? I should get your feedback. Does this make sense? Yes or no answers will suffice if you want. Okay, awesome. Yeah, so this is our setup. What we did is we created a better cost, but in order to minimize that cost, we needed to predict future states. And to do that, we need dynamics. So we have a quadratic cost function, and we have our linear dynamics. And now we have a linear quadratic regulator. And this is LQR. It's a super famous algorithm. It's crazy, awesome, and dope, and it's super useful. And it's called that because linear comes from linear dynamics, quadratic comes from quadratic cost, and regulator, I have no idea where that comes from. And our goal is to find the actions that will minimize this. Now, I don't think we have time to get into the weeds of it. The mathematical derivation is very much in the weeds, and it's also really cool. I might just talk about the ideas of it. You can ignore the actual, like the whole bunch of notation. But feel free to look this up if you want, or ask me on Piazza. Since the cost is a sum of costs, we can decompose it into the present, into the current cost, and the next ones. And what we can see is if we look at the very last state at like t, there are no next states. So it becomes a much easier problem. We just have the quadratic cost, and we don't have to do any prediction. And what that ends up giving us is we can basically actually solve the minimization problem algebraically for what u should be. And u ends up being a linear function. U ends up being a linear function on x. And what this does, which you can show mathematically, is that if you look at the state right before, the cost function is going to be a sum of the current quadratic cost and the next cost. And this will be the next cost. It's just we already computed what it is, and we know how to optimize this. And this will be optimized in terms of the next state. So the next action is linear on the next state. So if we look at the action right before that, we can basically merge this term over here into the quadratic cost, because since this is a quadratic cost and the action is linear on the current x, and the x is also linear on the current x, since we have linear dynamics. I mean, this is probably not making sense because I'm using words and they're jumbling, but this whole thing ends up being quadratic on x and u. And we can then make our second minimization problem equivalent to the first one, but just replacing what our cost is with different matrices that take into account what we would do in the next step. And we can basically use this to inductively go back every state until we reach the current state. And it all ends up being, the action always ends up being a linear, the u ends up being linear on x. And this is really nice, a very elegant solution. Basically, given linear dynamics and quadratic cost, we can roll out this backwards rollout through time, what the optimization problem would be to find out what the optimal action right now should be, and at every state following. And it's always going to be just linear on the state. It's going to be some matrix times the state, given linear dynamics and quadratic cost. And there's a bunch of variations to this. We can do a bunch of fixes, like if we have systems that are more probabilistic, instead of the dynamics being determined, it might be like a probability distribution of what the next state will be. Or if we have nonlinear dynamics, I mentioned, we will be using linear approximations. And we can take care of all of that. We'll actually be using, in the homework, you'll be using an implementation that Brandon made of iterative LQR. Iterative LQR, it just approximates nonlinear dynamics with the Taylor expansion. You don't have to program this, but you can use it. And what it does is, since this approximation is around a current state in action, a Taylor expansion is an expansion around something, you just initialize it to do LQR around where you are right now and what action you're going to take. But then as you optimize, you find better states and better actions. That's a good question. So I'll get to that in a second. As you optimize, you can get better actions, which will lead to different states. And then what you can do is you can recompute LQR but center your Taylor expansion around those states and actions. And this will basically give you better and better approximation as you get better and better actions and states. So iterative LQR will perform LQR, then update where it does the expansion around, and then do it again a bunch of times until it gets a really great trajectory. And that's the idea of it. And I'm just telling you about this because you can use it in the homework. Okay, yeah, so Alina asked what values go into Q and R, how are they calculated? This is a great question, and this will be something that you'll be doing in the LQR portion of the homework. So Q and R, Q represents the quadratic cost on the state, and R represents the quadratic cost on the action. So if we say our action is a steering and a velocity, a steering and a throttle, a vector of two numbers, a steering and throttle, then R is going to be a 2x2 matrix where, let's say it's diagonal. The first diagonal term is going to tell you how much do you weigh the squared steering action, and the second diagonal term is going to tell you how much you weigh the square of the throttle action. And say we don't really care if our car turns a lot, but we care if it slams on the gas. Then what we can do is we can basically, this is sort of like the PID tuning, to be honest. It's not very, this is part of the problem definition. So this is not something we like compute. This is just something we put in. So you can say, oh, I care about, and they're all relative. So what really matters is the relative values of these different elements. So we can say we really care about minimizing situations where we slam on the gas, but we're okay with turning a lot. Then we can have a higher constant for that than for steering than throttle. And what you would do is you would run LQR with that cost, see how it behaves, and see if it does what you wanted it to do. And if you find out that actually the car is swerving around like a maniac, then you can change those constants to penalize steering more. So yeah, you sort of have to handpick this cost function to do what you want it to do, which is basically trying to better communicate what behavior do you want. And if you can communicate that precisely by just by choosing what elements of the state and action we want to penalize, then it will find the optimal behavior. Does that answer your question? Does that make sense?
Yeah, thank you.
Awesome. Okay, so after a lot of talking, we reached the end of the lecture. Oh, let's look at cool videos. So as I've been saying, PID works for most tasks. It's very quick to implement. It's like we did live. You can interpret what it's doing. It's great. But it's sort of the finickiness of tuning it and the fact that it doesn't always work. And the tuning means we want to be able to do better. So if we model the dynamics of the system, the dynamics being the physics, being able to predict what future states are, this is super useful. I actually, when I was working at a self-driving car place, we ran a self-driving car, not with optimal control, but we just had a dynamics model, which better predicted how a car would behave and how it would turn. And using that, we hand-tuned control loop, much like that's sort of similar to PID, but aware of future states. And with slow driving, it worked great. But optimally, what you want to do is you want to get optimal control. If you define a cost function that will tell you exactly what optimal behavior is, which would be minimizing the cost function, you can derive what the actions should be to get there. And LQR will take your breath away, but it's expensive to compute when you compute it for many time steps looking ahead. And remember, LQR, we had a fixed number of time steps that we looked ahead. So, and we can tune it by editing our cost. So now I'll show you what I mean by it'll take your breath away. Here are some examples. This is maybe not the ones that will take your breath away, but just using LQR. So if we know what our desired states are, say for this unicycle, it's like stay stable or drive forward. It's still a really hard task to actually make it do that. And this is sort of an exaggerated system. In the car, it's not as difficult if we have a trajectory, but there's a lot of work to be done between having a trajectory and executing it. And LQR is what does that. So just by trying to minimize the cost function and getting to the goal state, there's a lot of real-time corrections that need to be done as you read in from sensors and update your state. And this is what LQR is good for. Self-balancing. Oh, we can swing a pendulum up, which is also cool. And when he pushes it, oh, that doesn't work. Okay, whatever. And with model predictive control, which is sort of an extension of LQR, where instead of having a constant like deadline of how far we look ahead and starting from the deadline and going backwards, we have a receding horizon where we can constantly compute like t time steps ahead. We can get really cool stuff. And this is, we're able to do this in here, the stuff you're seeing, because we have an exact model of the physics. We know, we program the physics and we know exactly what the physics are. So if you know exactly what the physics are, you can get truly optimal control. In reality, we're going to have imperfect models, and the better the model, the better your control system is. But this really shows that you can do, optimal control is amazing if you have the right models and the right cost. You can do things that are sort of crazy. This is more like this is a pendulum swinging, and then when we turn on the control, it'll balance itself. Bam. This is with random external forces and all that. Let's see, there's you're pushing this. This guy's really cool. He does flips. Yeah. And this is not a lecture, so if you have any questions, feel free to ask. Yeah, so this is by planning future states and minimizing a cost, we can get really precise actions. Yeah. So, any more questions? This is a lot of content. Again, I flashed a bit of math of LQR, and it's not, that stuff is just if you want to look into it, it'll be available. The PID math is hopefully intuitive enough that you can tune it. You'll be tuning your own PID loops, and PID tuning is a sort of like a rite of passage. So this is control theory. For homework, you're going to be implementing a PID controller in Duckytown to follow the waypoints that you generated from the path planning algorithm. You can pick what errors you want to use, like say the cross-track error or the different angle, and you can have a desired velocity or distance to the next waypoint. We're going to use some skeleton code for that, and you can also play around with iterative LQR by defining a cost function and running the LQR solver to minimize your cost function and seeing what it outputs. And this will be pretty computationally intensive. And I'll announce this on Piazza when I post it. Yeah. Let me pop this up. We can just look at model predictive control some more. Yeah, control theory is cool. And this is all computed just from a model of physics and a cost, which is, say, like height and stability, and probably in this case. It's not like they taught it like, oh, you should be moving your arms in this way to do a flip. That's really cool. And combined with complex trajectories, which model predictive control, this probably does use some of those, which we did with our path planning, we can get some great self-driving. Better than humans sometimes. Yeah. Okay. So I'm going to end the lecture there. I'm going to be on Piazza. If you have any questions, am I available to answer homework 5 questions? Oh, this is private. And I'm sharing my screen. Okay. Well, yeah. Okay. I'm going to, sorry, let me go back to, let me stop sharing. Okay, yeah. Thank you for coming to lecture. This is going to be posted on the Piazza, the recording as well. And good night.